Hello, guys. Today we'll be looking at very important concepts on. So first we have got the concepts of graphs. Graphs are very integral to mathematics as well as physics. We'll be surprised how many applications rely really on the basics of graphs. The reason this workshop is being taken um, mainly is to make the students familiar with the basic mathematics that is involved for solving any of the concepts in physics. Many times students directly enter the 11th standard without these basics and they're quite confused. They are in a struggle about the entire physics eventually and find the same basics troubling them over and over again. This workshop is intended to clear those basics and give a perspective to the student as to how such concepts can really make the subject very familiar. It has got nothing to do with physics in one sense. Uh, and we'll discover that slowly as we proceed through the workshop. By the end of this workshop, you'll be able to really completely understand what it takes to read a graph, right? You'll understand the language in which the subject has been presented. You'll understand how to uh, know from the graph whether the object is in a positive whether the object is accelerating or retarding, or for a given situation, how would the graphs of position versus time, velocity versus time, etc. would look like. Okay, and at the same time you'll be able to understand what these terms velocity, acceleration really are meant to describe, and the interrelation between them both differentially and graphically. So this is a unique kind of a presentation which will equip you with all the relevant skills necessary to solve the problems. As we solve the problems, as we understand the derivations, we'll make ourselves very comfortable with these applications. Okay, so without wasting further time, let's start here. The first the first thing we'll be equipping ourselves is the few of the definitions of the kinematic variables first. Then we'll come back to the immediately shortly we'll come back to the graphical interpretation of those of in generic graphical interpretation, because we'll be building the context here why we are doing these uh, things. Okay, to start off, we'll be starting with a basic demonstration here, which is slope. So first thing here, suppose I tell you there is a graph y equals to f of x, or there's a function y equals to f of x. What it means, anytime I say from here on, these are few things which will remain, which we will have to remember. Any value y equals to f of x here refers actually to the uh, it refers to the, you know, certain transformation on x, or in one sense it's an output on x, where x is your input and f of x is your output. If I give x equals to 1, let's say f of x equals to 2. If I say x equals to 2, let's say f of x equals to 4. If I say x equals to 3 and let's say f of x equals to 6, what exactly is happening here is the function f of x is multiplying the x with 2. So we say such a function f of x as f of x equals to 2x. Now, with this context, you can take the idea of transforming the input to an output. So that is called as a function. We call this particular idea. Now, the function could be anything. It could be a polynomial function. It could be a logarithmic function. It could be even a exponential function, depending on whether you are making such, what kind of transformation whether you are making, or it could be it could be a sinusoidal function, etc. We'll be first making ourselves comfortable with a polynomial kind of function. What is a polynomial kind of a function? A function that is of the notion a0 plus a1x plus a2x square plus a3x cube. So these are called polynomials, right? So when I When I have a polynomial function, all I have is algebraic multiplication of the variables. When I say I have a logarithmic function, I have the log function here, log x. When I say exponential function, I have e power x. So the transformation here is exponential. So for x equals to 1, the output would be e. For x equals to 2, the output would be e square. And the same idea can hold true for any kind of other functions. So with this generic representation, say I have a function f of x. I would like to now see how this function is varying with x, right? So before that, let us understand how the variation can be understood, right? We could understand the variation in a lot of ways. One of the simplest ways is to understand it through a graph. Let's say here I have a function y equals to x. So as you see, it's just a straight line because at each and every point, when x equals to 2 here, y is 2. When x equals to 4, y is 4. When x equals to any other value, it's the same value for y. Now at the same time, let's say my graph is y equals to 2x. As you see, for x equals to 2, the value of y is 4. Now this is a point 2 comma 4 which is on the graph here. Similarly, for x equals to 3, y is 6. Now I can understand for x equals to 5, y is 10. So in general, if I have y equals to mx with a slider for m, I can see how this graphs, how these functions could create the variation in the graphs. Let's say I change the value of m. You can see how the function is changing, right? Now, one thing that you notice as m increases, you'll notice that basically the value of angle here is increasing as I increase the value m, isn't it? Now, as I reduce the value of m, what's happening here? You can see as I reduce the value of m, the angle here is decreasing. Now, this is something which is telling us about a generic kind of functions. These are called as linear functions. So now when y equals to mx, we have understood two things. That first of all, y equals to mx is a generic representation of a certain kind of functions. What are they? They are polynomial functions. And in the polynomial functions, whenever I don't have the other higher order terms, it's just called as a linear function. One subset variation of a polynomial function is a linear function. So y equals to mx is a generic representation for a linear function, which means I just don't have the other higher order terms. Okay, let's see something else. Let's understand that this value of m here is representing us certain information on the angle theta. But what is this theta going to help us with, right? If I have to tell that this function at a if I increase the function by one value on the x, by how much will the y increase? If I have to tell you that information, like you could say, if I increase the x by 10, how much would the y increase? When it's an identity function, I'm very sure that it is going to be 10, because when x increased from 10 to 20, y would also increase from 10 to 20. So then in that case, I know that when the change in y by change in x, that ratio is 1. You can see that that ratio is what is being represented by this angle here, which is called as the tan theta. The change in y by change in x, it is expressed as tan theta. As we would understand, in this particular graph here, we can notice this is the del, x change in x. This is the del y, change in y. And the ratio here, del y by del x, is somewhat related to this theta that we have been looking at, which is your tan theta. This tan theta is hence your slope, which we say dy by dx as well. Dy by dx corresponds to the same tan theta, the same del y by del x, but with the value del x becoming very, very close, very, very small, which means as you have seen here, I've taken interval very long, del x equals to 10. Instead, I would like to deal actually with a very small intervals, because quite often for other polynomial functions, the line or the curve changes very rapidly. It's not going to be in the similar fashion as you see here for a linear function. This value del y by del x at this point, when x tends to 0, when delta x tends to 0, is called as dy by dx. So we could understand dy by dx as being the slope at a given point itself, because the delta x is so small that I could consider it belonging to that point. So therefore I could say, whenever I have a linear function of the form y equals to mx plus c or y equals to mx, right? I could say this value m is the same as dy by dx. So the value here that you see, m, is nothing but dy by dx. So as m increases, you would notice here that the inclination here, the theta increases, which also implies that dy by dx, which I say here, is equal to tan of the theta. Because in this curve, as you can see, delta y by delta x is nothing but tan theta. So therefore, the value dy by dx can also be said to be equal to tan theta. And because it's a straight line, we know for a straight line the value of theta at any given point is the same, because the straight line is one where it's making the same angle theta with any for any set of parallel lines. Hence, we can also say based on this that the slope is constant for a straight line. Which is very intuitive to understand. Slope being constant for a straight line is something we all can very intuitively understand, because on in a slider, when the person is sliding in a slider, if the slope is constant, his rate more or less would be uniform. However, if you just translate it in the sense for the functions, you could say for a linear function the slope is constant, because we could have functions which are polynomial in nature and which are where the the curves are changing at a different rate at each and every point. Let's for instance take this polynomial here. Now it's a quadratic or a cubic function which cannot be, we cannot ascertain any particular relation at the moment, but we can be sure that at each and every point here the value of this theta is changing. So one way to get the value of the slope for a polynomial function is to draw the tangent at that given point. So now when the tangent would intersect the x-axis at a particular angle, that would be the theta of this particular point. That would be the slope. The tan of this angle theta would be the slope at this particular point. How did we get the, just like we can say the slope here is constant, how do we know how the slope changes for each and every point here? Is there a specific relation? Yes, there could be a specific relation how the slope changes. That depends on the polynomial. But we could be sure that this value of slope at a given point can be obtained by just computing this value, limit delta x tends to 0 delta y by delta x, which is equal to dy by dx, which is the slope at this point, which is going to be the slope, which is going to be the slope of the straight line of a tangent at that point. Slope of a straight line at a tangent slope of this straight line, right, which is a tangent at a given point. There would be a definite variation of the slope itself, because we can see when there is a polynomial using this definition of slope, if you could compute a certain relation for the slope as well based on the polynomial's equation, that would that could help us to generalize how the slope varies at each and every point. This is basically called calculus, and the calculus has got certain mechanisms which we are not discussing at this point to compute the values of variations for different kinds of functions. At this point, we can see, for instance, if I have a uh, we are not going to deal with this methodology to compute the slopes of different functions, but what we would be looking at is only for a curve computing the value of the slope based on drawing a tangent. As you can see here, slope of any given point could be computed just by drawing the tangent at that point and calculating the slope of it. How would we calculate the slope of a tangent? As we know, slope of a tangent is nothing but slope of a straight line, which can be obtained by just calculating tan theta. So here the angle theta made with the x-axis here would be the slope of this tangent, which means that is going to be the slope of this curve at this given point. Let's take a small example. Let's see a curve which is varying in this fashion, ABD. Now to compute the slope of the tangent at a given point A, what has to be done? I'll just have to do, or to compute the differential. Okay, the question is to find the differential dv by dx at x equals to 2. To find this, I would have to compute the slope of the tangent at this given point A. How can we do that? We can just do that by drawing a straight line here, and we know the value of the delta y here equals to from 0 to 4. So it's 4. Similarly, the value of delta x here equals to from minus 2 to 2. That's also 4. So point, slope of the curve at this point a dy by dx should be equal to the slope of this line, I, slope of the tangent at a. That value equals to tan theta 1, which is equals to delta y by delta x, which is 1. Hence, I'll say that the slope of this point a is 1. Let's find the value of dy by dx at x equals to 6, which is the point P. At x equals to 6, we can see that the value, the tangent here appears to be parallel to the x-axis. Now, when a line is parallel to the x-axis, there is no variation in y. So for such a line parallel to x-axis has got a zero slope, as there is no variation in y. For any amount of variation of x, the value of y is not changing. Y is a constant. Hence, the value of the slope at this point P is equal to 0. Let's find the value of the slope at x equals to 10, which is the point D. Now, the slope of this curve at the point D should be equal to the slope of the tangent at D. The slope of the tangent at D is computed by just finding the value of delta y by delta x once again. The tan theta 2 here would be equal to delta y by delta x, which is 4 by 4. Normally, we would be expecting the slope to be equal to 1. However, we know here that tan theta 2 is the complementary angle to the theta 2 that we have found. Let's call it tan theta 2 dash. Tan theta 2 dash would be delta y by delta x, which is 4 by 4, which is 1. This tan theta 2, which is the value of the angle made by the line which is tangent at D, is an obtuse angle. So tan theta 2 should be equal to tan 180 minus theta 2 dash, which implies tan theta 2 is minus tan theta 2 dash. Therefore, we know that the slope should be minus 1. So we can understand from here that there are two values of theta. We could segregate into two values of theta. One is the angle between 0 to 90 degrees, and the other segregation is between 90 to 180. This here is open, this is closed, this is open, this is closed. For these values, the slope here appears to be positive. For these values here, slope is negative. The value of the slope at 90 degrees is not defined, or it is infinity, and it has no practical value at this moment. There is an other important information contained within the differentials, which is called as representation of concavity, or in general, to summarize it, it's telling us how the depending on the graph, which appears either this way or this way. In one sense, it's called as a concave up graph, and the other is called a concave down graph, which means it's concave towards the downside, is concave towards the upside. We could be having a lot of different variations, but this particular concavity is represented by a term called as d square y by dx square, which is the curvature. As we know, dy by dx is representing as a slope. Similarly, there is a certain amount of information contained in this d square y by dx square. We'll look at it more as we encounter the graphical variations. Now, as have been, as we have discussed here, we could be having a lot of different kinds of functions whose differentials we could be computing using this definition, which is the fundamental definition in calculus, and we have a tabulated results of various kinds of functions that can be seen here. For a function y equals to x power n, the differential is computed and it equals nx power n minus 1. For a function y equals to sin x, the differential is cos x. And for a function cos x, it is minus sin x. Likewise, for different kinds of functions, we have already computed the differentials and we have tabulated these results, which are available for us for our use. At the moment, we'll be also looking at certain other transformations in differentials. The differential operation for a variable cy. Let's say I have to compute the value of differential of cy. So I would be doing d by dx of cy. Now what I'm interested in is basically find how cy would vary with respect to x. But since I already know that if I have a curve of y versus x, and if I just multiply y with a constant, what is going to happen? It's just it's just like the value of delta y being multiplied with a constant for a given delta x, which means whatever is the slope here, the slope gets multiplied by the same constant you are multiplying the y with. So therefore, the c here has come outside of the differential, and we just multiply c times dy by dx. So similarly, when I have two functions u and v whose differentials I'm taking with respect to x, d by dx of u plus v. Now by the differential rule, I could write it as du by dx plus dv by dx. This is basically because if I have delta of u plus v, I could easily add the two changes delta u plus delta v. So delta of u plus v with respect to delta divided by delta x would be equal to delta u by delta x plus delta v by delta x. Now this, when limit delta x tends to 0, would be du by dx. This would be dv by dx. Similarly, for the product rule, d by dx of uv. Note here, d by dx of uv is not like this, because del of uv divided by delta x cannot be written as del u by del x into del v by del x. These two are dimensionally different. We could not compare, we cannot have any comparison between these two. Therefore, what is the way to approach this is by finding out del of uv. Once you do that, we would arrive at such a relation: u del v by del x plus v del u by del x. Similarly, d by dx of u by v. In place of v, when we substitute 1 by v here, we would get the similar result: v du by dx minus u dv by dx by v square. And the last one, a very important one, called as a chain rule in differential. Anytime we have to find the differential with respect to x, and that variable is going to be indirectly affecting the variable y, we could compute another intermittent variable u which varies directly with y and compute the differential in this fashion. This is called as the chain rule. Notice that we could always divide whenever we have delta y by delta x, we could always multiply and divide by delta u, and that would be the same as del y by del u into del u by del x. When you apply the limits, you would notice this would turn out to be dy by du into this would turn out to be du by dx. Let's use these particular differentials in the physical context. All along we have defined and we have used certain important functions in mathematics, and we have defined their differentials. How would that apply to the physics that we are going to deal with? So in physics, we know that we have a term called displacement, which is in essence telling us the shortest distance from a given point to another point. Let's not let's define it by a value s. We know that the velocity is the definition of velocity is rate of change of displacement, ds by dt. For now, let's consider a straight line motion, a 1D motion, and it's going in one direction. So I would say the value of s displacement would just become your distance. Therefore, the value of velocity would now be ds by dt, and acceleration would be d square s by dt square. As you see, these are differentials upon displacement. Because we know acceleration is the rate of change of velocity, if I had defined velocity as v, the acceleration would be defined as dv by dt. And because acceleration is dv by dt, it's going to be d square s by dt square, because it's the differential of the differential on s. Now, with these definitions and with the help of few standard derivatives that we have already looked at, let's solve certain questions here. First, a particle is moving with a speed v equals to b root x along positive x-axis. Calculate the speed of the particle at time t equals to tau. We know at t equals to tau, we got to find the value of the the speed of the particle, and assume that the particle is at origin at t equals to 0. So x equals to 0 at t equals to 0. This is one set of applications we are looking at in 1D motion. Most often you will find such questions which are becoming increasingly popular in the recent years. In the last 3 years, we have seen certain amount of shift towards such kind of questions involving the definitions of velocity, acceleration, displacement. That is the very reason we are looking at this particular thing in the beginning itself, this concept at the beginning. You can see here, I just have to use the definition in order to find the value of the speed, which is dv by dt. And I know dv by dt is supposed to be d by dt of b root x. But I see that the function which I'm talking of here is b root x. and it has got no relation on with t. But I understand that definitely it has got an indirect relation with t. Therefore, I do the chain rule, which is d by dx of b root x multiplied by dx by dt. That would be my dv by dt. D by dx of b root x is going to be b b times x power 1 by 2 d by dx. If we refer to our table that we have already looked at here, whenever I have y as x power n, dy by dx is supposed to be nx power n minus 1. So let's use that here. Because I already have y as x bx power 1 by 2, my value of dx power 1 by 2 by dx is going to be n, which is 1 by 2, x power n minus 1, which is 1 by 2 minus 1. That is going to be 1 by 2 root over x. Now we'll also use one more rule here of differentials, that is the c, which is constant multiplying y, comes outside of the differential. Therefore, I would have to just take out this b outside. So this would become b divided by 2 root x times dx divided by dt equals dv divided by dt. What is this value dx by dt? We already have the information dx by dt is v. So I could write this as dv by dt equals to v into b by 2 root x. I could just bring up this. Uh, this has given us that this has given us the value of acceleration varying with respect to v and x. I see that I'm not in a position to go any forward from here because I've got three variables. I've got a differential of v, I've got a v, I've got a x. So I would like to simplify this situation even more by taking the differential definition of v in first place and dealing with displacement. V is nothing but dx by dt. Dx by dt is given as b root over x. Now in order for me to get the value of x, I would have to use dx by b root x equals to dt. How should I proceed from here? The main, as we have seen here so far, we don't have a valid answer to proceed here. That's where the integration comes into picture, which we'll be looking at in a moment from now. That is why we define integration, which is just the opposite of differentials. Don't you see here that if I had a if I would somehow find the value which which tells me uh, how my x could depend on time, such that my dx by dt would be the same as b root x. Here, as you can note, dx by dt is b root x here. I would like to find the value of x which depends on time. That would give me this b root x in return. So this can be accomplished by finding the integral of this value, dx by b root x equals to dt. We'll see that in a moment. We'll come back to this question after we look at the integration, and then we are going to see how to solve this. Let's take another question here. A particle at x equals to 0, at t equals to 0, and starts moving along the positive x direction with a speed v that varies with displacement as alpha root x. Now the displacement of the particle varies with time as you see here, this is the exact same kind of question as we are dealing with at the moment now. V is b root x, v is alpha root x. This is an interesting thing with respect to the repetition. Let's come back to this problem after, as we said, after we do with the integration. Now here we can see here that the displacement varies with time as at plus bt square minus ct cube, where abc are constants. Now we are asked to find, when the particle has got zero acceleration, the velocity of the particle. We are asked to find the relation of velocity when the acceleration is zero. First, let us compute the value of velocity, the dependency. The function is varying. It's a polynomial function, as we can see from our discussion. We have just discussed the first thing, which is a polynomial function like this. Now, is there a way I can use the standard functions, standard differentials of the functions, and compute the value of differential here? I could. Dx by dt is supposed to be d by dt of at plus bt square minus ct cube. What would this be? D by dt of at plus d by dt of bt square plus d by dt of minus ct cube. What would this be? D by dt of at. A is a constant, take it outside. A times d by dt of t, which is 1. Plus d by dt of bt square. B is a constant, take it outside. D by dt of t square. A very interesting thing here, how did I get this one? See, always remember dt by dt, you could just cancel them, because delta x by delta x, as we know, we could just cancel it. D by dt of t square. What is d by dt of t square? D by dt of t square is nothing but, we could use the same relation that we have earlier, which is d by dx of x power n, nx power n minus 1. As you can use it, as we use the same relation, we would get here as b into 2 into t, because n is 2, n t power n minus 1, which is 2t. Similarly, d by dt of minus ct cube, which is minus c into d by dt of t cube. We know this as 3, n here is 3. D by dt of t cube is supposed to be n x power n minus 1. X here is t. So the relation is 2bt minus 3c into t square. This is our value dx by dt, or velocity v. The value we want now is the acceleration. To get there, I have to do one more differential, dv by dt. What would that be? D by dt of 2bt minus 3ct square. What would this be? D by dt of 2bt. 2b is a constant. Take it outside, multiplied by d by dt of t, which is 1. Once again, I have to do the differential. 3c, take it outside, into d by dt of t square, which is 2t. Hence, I have the value 2b minus 6ct. That is my acceleration A. Given a condition that the particle attains zero acceleration, what its velocity is. So equate that condition what is being given, a equals to 0. So we have 2b minus 6c t equals to 0, or in other sense, otherwise t should be equals to 2b by 6c. This is b by 3c. If I use this value of t here in the equation, in the expression for v, I would get the value of velocity. If I substitute v equals to 2b into b by 3c minus 3c into t square, which is b by 3c whole square. This is 2b square by 3c minus 3bc 3b square c divided by 9c square. C and c square gets cancelled. This value would therefore be equals to 2b square by 3c minus 3b square by 9c, which is nothing but 6b square minus 3b square divided by 9c. 3b square by 9c, b square by 3c. Now also we have this a here. So if we add that a, our answer should be b square by 3c plus a. From the options we could see that it is option B. Now let's go to the integration. How can we understand integration? As integration is basically the differential, the reverse of differentials. So if I have a curve dv by dt is a and dx by dt is b, so the same things in the reverse order would be your integration. That is, if a is dv by dt, I could say the graph of a versus t is v, or in other words, integral a dt equals to v. So it's the opposite of differential, because a is obtained by differentiating v with t, and I would obtain v by integrating a with t. So integral a dt is v, which in other means also refers to the area under a versus t as v. So from t1 to t2, if I want to find the value of velocity at t2, what would that be equal to? It's obtained by just computing the change in velocity from t1 to t2 is obtained by computing the area of a versus t, right? So the shaded region here represents the value of delta v from t1 to t2. So therefore integral a dt t1 to t2 is nothing but v2 minus v1. At the same time, integral v dt should be my displacement, because v versus t, because dx by dt is v, that implies integral v dt should be equal to the displacement x. Therefore this area would correspond to x2 minus x1, which is integral v dt. Just like differentials, even integrations have got a standard functional. So integral x power n dx is given by the relation n x power, I'm sorry, n plus 1 into x power n plus 1 by n plus 1. Now this is a simple formula which we can use any time to find the value of integral of a function. This can be verified here by computing the same, by finding out that the differentials of this would be equal to the value x power n. As we can see, if I differentiate d by dx of x power n plus by n plus 1, it is going to be, 1 by n plus 1 is a constant, take it outside. So d by dx of x power n plus 1, and this value is supposed to be n plus 1 x power n. These are getting cancelled out. So the value x power n is my value of the differentials, is the same value here. Therefore, I can say if d by dx of this function equals to x power n, I could say the integral of x power n dx equals to x power n plus 1 divided by n plus 1. as per the definition of integration, which is just the reverse of differentials. Similarly, we could also compute and say integral x power n dx is equal to x power n plus 1 by n plus 1 plus a constant c. So if we go back to the standard derivatives that we have already seen, if I have dy by dx of x power n, dx power n by dx is nx power n minus 1, then I could say integral nx power n minus 1 is x power n. And similarly, I could say integral of cos x dx is sin x. If I just reverse the tables, if I just interchange these tables, then I have to change the operator of differential to integration, which means if I draw a table for integ for integral dy by dx into dx, as we see integral dy by dx into dx is nothing but delta y. Hence, the dy by dx if is cos x, then integral cos x dx should be equal to sin x. And if I have the limits here going from, let's say, x2 and x1, the same limits apply here. Sin x2 minus sin x1. Upper limit minus lower limit. So that would be, I'm sorry, this is x2 and this is x1. Then it would be sin x2 minus sin x1. Let's use this to compute this. The speed varies as shown in the figure. The distance traveled in meters by the particle during the time interval t equals to 0 to t equals to 5. From 0 to 5, we got to compute the distance traveled by the particle. As we know this is a speed versus time graph, then I could say the distance value is supposed to be equal to integral u dt, or area under u versus t. This is u versus t, so if I compute the area, that should be my distance d. Now what is the area of this triangle? Which is going to be half base, which is 5, into the height, which is 8. This is 20 meters. Hence I can say that the distance traveled by the particle from t equals to 0 to t equals to 5 seconds is 20 meters. This covers the basics of calculus in 1D motion. Let's see graphically how we could relate the basic functions. So at this point we're going into the second part of our seminar here. So we have seen firstly a function y equals to mx, which is a linear representation, can be shown with a straight line. What if I have a function like a polynomial, say a plus b x, or let's take a polynomial, the simplest polynomial we could take off is x power 2 x square. This is y equals to x square. As we see, it's a curve, it's no longer a straight line, it's curving like this, and it is supposed to be symmetric about y axis. Let's take y equals to x cubed. A small change from the previous function. This function y equals to x cubed turns out to be symmetric about, it is actually, it's like a reflection about the line passing diagonally from the second and the fourth quadrants. Likewise, you'll notice when I have once again x power 4, it's once again symmetric about the y-axis. If I have x power 5, you'll notice it's once again like the x cube function. So these are called as the even and the odd functions. What are even functions? Even functions is when I have the exponent as an even number. So whenever I have an even function, you'll notice that it is exactly symmetric about the y-axis. What is so unique about an even function? You'll notice that for a positive value or for a negative value, the value of y would be the same. This value of y can never become negative. Hence, the graph is a symmetric function about the y-axis, because for the plus x and for the minus x, you'll have the same values. Similarly, just notice y equals to x power 6, y equals to x power 8. everything is just going to be a even function like this. As you notice, as the power of x increases, the flatness of the curve increases. Now let's look at the odd functions, x cubed or y equals to x power 5 or y equals to x power 7 or y equals to x power 9. Whenever the exponent is odd, that's called an odd function, because for the odd function I would have a negative value for the corresponding negative value of x. Let's say y equals to 2, the value of x, when x equals to 2, the value of y in a y equals to x cubed function has to be 8. When x is 2, y is 8. But when the same x is minus 2, y will have the same magnitude, but it is going to be minus 8. Hence the curve is just going to be symmetric about the values, but it cannot be symmetric about the it's like it's the same function, but it is inverted with respect. It's a mirror image about this particular line, we could say, in one sense. But essentially it exists in two quadrants, that is the first quadrant and the third quadrant. It does not exist in the second quadrant, because when x is negative, the value of y is negative. Something which is interesting is if I take a function y equals to x square, and let's say add another function uh, which is y equals to x power 1 by 2. So we'll notice here that the two functions y equals to x square, y equals to x power 1 by 2 appears to be like a mirror image about x equals to y. Let's say I have y equals to, let's take y equals to x cubed, and let's take y equals to x power 1 by 3. We'll notice this much more prominently here, that y equals to x cubed and y equals to x power 1 by 3 appears like a mirror image about this line x equals to y. Let's say I have y equals to x power 4, y equals to x power 1 by 4. As we notice, the values of these two functions appear to be like a mirror image about this line x equals to y. They're exactly symmetric here. And as you go here, they'll be symmetric here as well. And similarly, if I have x power 5, I would have these two functions once again as a mirror images here. So I could say therefore that whenever I have a function y equals to x power n and y equals to x power 1 by n, I could say these two are inverse functions. Inverse function would simply mean that for the corresponding value of uh, for the corresponding value of x, if I substitute the output of one function if I substitute the output y equals to x power n, I know that x corresponding to that is supposed to be y power 1 by n. If I have the value of y, the corresponding x is x equals to y power 1 by n. Now for that value of y, this is the same as this function, which is y equals to x power 1 by n. So that means for this value of y, if I keep the value for this particular y, if I use it in this particular function as an input, I would get y equals to x. These are called as inverse functions, because f of g of x would be the same x. Now in such cases we would say that the g of x function is called the inverse function of f of x. and such graphs. To understand this graphically, the graphs would be of this form, wherein there would be like a reflection about y equals to f of x, like a mirror image about y equals to f of x. If I have to draw another curve which is y equals to x, you would notice that that is perfectly symmetric about these two graphs. So if this blue line were to be a mirror, then y equals to x power 5 and y equals to x power 1 by 5 would be just like the mirror object and the image of this particular about this particular mirror. Let's understand a little bit about certain other kinds of functions. Let's take a circle. Y circle is quite often represented by x square plus y square equals to constant. So any expression of this form, x square plus y square equals to a square, becomes a circle. Now let's also see how the circles, what are the other generic notations of a circular expression. We could also say x minus 2 whole square plus y minus 2 whole square equals to 4 is also a circle, just that it's a displaced circle. The center of the previous circle is 0 comma 0, as you can notice, but the center of the new circle turns out to be 2 comma 2. As you see, the reason is because of the displaced center. Whenever if you had changed the origin from 0 comma 0 to this point 2 comma 2, then this circle would also be the same value x square plus y square, because in essence we have to understand the value of x is basically the distance from the origin. So when you take x minus 2 whole square, you are moving the origin by 2 paces to the right, to this location 2, and you are moving the position of the origin of y axis to this position 2. Hence, with respect to these 2 points 2 comma 2, you would have the same equation, that is x square plus y square. Hence this particular equation would also look like a circle, but just that we would not have a direct relation like x square plus y square equals to 4. So the same thing can apply to a straight line as well. Just like we have y equals to x, y equals to x power n, etc. We could also define the same relations with y equals to x minus 2 whole power n. That is, if I have a curve y equals to x square, it's symmetric about the y-axis, but if I have a curve y equals to x minus 2 whole square, I would have a curve that would be symmetric about x equals to 2. It's a displaced function from origin. The reason being, it's like the origin shifting from x equals to 0 to x equals to 2. Similarly, if I have a function y minus 2 equals to x square, that's like shifting the y origin to 2. So the graph would move up. These are certain examples of transformations. We can see a lot of transformations. For example, if I have a curve f of x, and if I want to find the graph of f of x plus or minus a, how would the graph look like? Let's say I have y equals to x square, and I want to find y equals to x square is my f of x. My f of x is x square. Now I want to find what is the graph of the function y equals to x square plus 4. As you see, it would be a graph that moves in the y-axis by 4 units up, because the base has gone as 0 comma 4. Similarly, if I have y equals to x square minus 4, we would notice that the graph would have gone down by the same 4 units. So whenever I have the transformation like f of x plus or minus a, the graph would just basically shift up or down. The same graph would shift up or down. This is known as the translation of the graph. Let's look at certain other transformations. The transformations of f of x plus or minus a, as we have discussed, is the shifting of the graphs. The shift would be to 2 comma 0 here because the shift is to the point 2. Let's understand the transformation a into f of x. A into f of x is like the same function, just that its slope would change. Let's say y equals to x and y equals to 2x. As we have already seen with respect to y equals to mx, the how the multiplier is affecting the value of the slopes. What about change of the variable from x to kx? In the linear case, we would get the same, but let's say I have y equals to x square, and let's say I have y equals to, let's say I have y equals to x minus 2 whole square. Let's say I have y equals to 2x minus 2 whole square. As you notice, the one change that we observe is the curve has become narrow. In other sense, the slope has increased at each of the points corresponding to the slope. Compared to x square, the value of the slope has increased. But if I have x by 2 minus 2 whole square, then you can see that the slope has decreased. What would happen instead of x? I have y equals to f of minus x. Let's say I have y equals to 2x, which is a straight line and positive slope. Y equals to minus 2x would be a straight line but with a negative slope. In case of the even functions, it doesn't matter, but in case of the odd functions like y equals to x cube, we have the curve which is in the first and the third quadrant, and you would notice that y equals to minus x cube would be a curve in the second and the fourth quadrants. Simple reason, because each time the value of y is inverted, the quadrant is shifted. Likewise, we could obtain the different transformations of these functions, and the corresponding graphs could be understood. How are these related really to the 1D motion? As we have already discussed earlier, that these things are very much related to the curvature, a concept which we are going to cover for 1D motion, a very important concept for 1D motion. How is curvature going to be reflecting the 1D motion? As I said, curvature tells us about the uh, rate of change. Let's take a case where let's say a graph that is going in this fashion. Now, as we have seen, this is like a polynomial function y equals to x power n, where n is greater than 1. Only then the curve would be going like this. Because one important thing to understand here is um, this curvature here is characterized by the value d square y by dx square, which means it is characterized by the increased rate of change of the slope. The slope at each and every point, how it changes, that is what is d square y by dx square dealing with. right? Because d square y by dx square, d square y by dx square is nothing but d by dx of dy by dx. dy by dx here is the slope value. Slope talks of the tangent at various points, but the d square y by dx square is the rate of change of slope, which is talking how the curve is going to vary. So as we see, whenever I have a concave upwards curve, the d square y by dx square is going to be greater than 0. So the curve upward could go in many ways. The function as such could be decreasing, the function as such could be increasing, but it is a concave upwards graph, which means it looks like a bowl like this. In such a graph, I could definitely say d square y by dx square is greater than 0, and therefore I know that such a curve will only have a minimum also. We'll come back to what is minimum, what is maximum. There's another kind of graph which is called as a convex upwards graph or a concave downwards graph, which means it looks like a inverted bowl. This is a convex upwards graph, or it looks like the surface of the earth or any of the spherical sphere from the outside. For such a curve, we have d square y by dx square less than 0. These are the only two things we got to remember. Lot of times students are confused with respect to how to take dy by dx, what is maximum, what are the conditions for minimum and maximum. Just remember, with respect to differentials, when d square y by dx square is less than 0, that's going to be a convex upwards graph, which means it's going to have a maximum, right? Now, for this graph, when when it has the maxima or the minima, you will notice that the slope will actually be 0. We'll come to that once again. Now let us see what all information we can gather from the displacement versus time. This is the first application we are going to see for the graphs as well as for the differentials in 1D motion. So we know, let's say the displacement versus time is, we can know basically these three things: the initial displacement, the velocity, and the acceleration. See, for example, the displacement versus time graph, let's say, is going like this. Now, this graph shows that at t equals to 0, the value of displacement is 0, right? That means the object was at origin itself. But if the same graph is just shifted upwards, let's say, right? Now this is like y equals to, I have, let's say, I have s equals to, s is my displacement, I have s equals to 2t. This is a graph that's passing through the origin. But if I have s equals to 2t plus 4, now that's like the transformation of this graph. It has to slide upwards by 4 units. 0, comma 4 is its starting point at the origin. So that means basically the initial value at t equals to 0 has changed from 0 to 4. Correct? That means what is that? That is the initial displacement. That means at t equals to 0, the object is not at the origin, right? So you have taken an origin, but at t equals to 0, the object, if you are interested in defining the object's position, or right, at t equals to 0, where is the object you want to find? Then this graph can help you. That is, at t equals to 0, you'll know that the object has got origin at 4 meters, or whatever the case may be. But one thing you'll notice is in these both cases, the value of the slope hasn't changed. Y equals to 2t, y equals to 2t plus 4. In both cases, the slope is still 2. That means the same graph has got translated. Translation doesn't change the slope. Therefore, the velocity versus time graph is also an information from the displacement versus time. How? What is the kind of transformation we got to do here? We got to find the slope of displacement versus time is your velocity. Slope of displacement versus time is ds by dt. This is your velocity versus time graph. As we can see here, since the slope is constant, the velocity versus time would be a constant graph. There's another kind of information that is obtained here from the displacement time graphs, which is our acceleration. As we know, the slope of dB by dt is your acceleration, or we could say the slope of the curvature of s versus t is your acceleration, which means if I have the displacement going like this, I would say that the curvature is positive. So in this case, what can I say, guys? The acceleration is positive. And similarly, if the curvature is negative, that is, if I have a curve like this, then I would say that the curve, if it's a, this is a concave upwards graph, guys, right? I would say in this case the acceleration is positive, and let's say I have a curvature up. I have like a convex upwards graph. This is like the curvature is negative, or basically the acceleration is negative. These are the two cases possible, right? Is there any other information that we could get from the displacement time graph? Well, let's try to use these particular concepts in 1D motion and the kinematics 1D motion. Let's try to understand certain standard cases of problems discussed with these particular concepts. First thing, or before we go there, let's go back to that problem which we have left out here. So as you see here, the value of dx by dt is b root x, and you can understand I could represent dx by b root x equals to dt, and I could integrate both sides. So if I integrate now, I can solve this using integration. As I said, this is how I will solve it. Integral dx by b root x, it's nothing but integral b root x dx. This is, I'm going to find that particular function which gives me b root x upon differentiating. So that's going to be b into, I told you already, integral x power n dx is supposed to be x power n plus 1 by n plus 1. So it's going to be b into x power 3 by 2 divided by 3 by 2. That is going to be integral of dt, which is t. So I see from here that the value of x can be written as, and of course this is going to be a limit, so 0 to t, and this is 0 to x. So when this is 0 to x and this is 0 to t, this is called as kind of applying the limits. So what we have to do is we have to just subtract the upper limit from the lower limit. So substitute the upper limit x, subtract the lower limit, which is 0. So that would give us the total value of the integral. Now we can understand here the value of x is changing, like x equals to 3 by 2 b into t power 2 by 3. 3 by 2b, 3t by 2b whole power 2 by 3. How would we find the velocity from this? Because here I'm interested in finding the speed. What is speed? Speed is dx by dt. Dx by dt from here just has to be the differential of this d by dt of 3 by 2b into t whole power 2 by 3. This is going to be 3 by 2b into t power whole power 2 by 3 multiplied by t power 2 by 3 and differential of it d by dt of that. This would be 3 by 2b whole power 2 by 3 times d by dt of t power 2 by 3 is 2 by 3 into t power 2 by 3 minus 1. That is your value of velocity v. We can notice the value is supposed to be I'm sorry, let's use the differential in a there's a small correction to be done. Integral dx by b root x is b into x power minus 1 by 2. If I use that particular relation, I'm going to have a different answer, which is what we got to correct it for. So the integral b x power minus 1 by 2 dx, x going from 0 to x, is supposed to be equals to b into x power 1 by 2 minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. This value is supposed to be equal to t. Now b into x power 1 by 2 divided by 1 by 2 is your t. So we can know from here that x is supposed to be 1 by 2b into t whole square, or that's t square by 4b square. That is x. Now if I want to find the with the limits, of course, used up here, 0 to x would be t square by 4b square. And if I have to find the value of v, then that's dx by dt. Dx by dt is supposed to be equal to, as we have seen earlier, when x is going as t square by 4b square, the dx by dt is supposed to be equal to d by dt of t square by 4b square, which is d by dt of, first of all, 1 by 4b square is a constant, take it outside, multiplied by d by dt of t square. That is 1 by 4b square into 2t, because we have already seen the differential of t square is 2t. Now 2 and 2 gets cancelled, so I have t by 2b square, that is my v. Substituting the value of t, I'll get the value of velocity, because I have to find the value of velocity at t equals to tau. Once again, this is a small correction here. The b is in the denominator, which means the b here is in the denominator, divided by b here. The same thing would go at each and every point here. The b that we are saying should be in the denominator, so it would be 1 by b here, and similarly the b that we are saying here should be in the denominator, which would be here 1 by b. Same thing here, this b should be here in the denominator. So now when I want to find x, the b when it goes here, it goes to the numerator. So my x is supposed to be b by 2 t whole and whole square. That would give me b square by 4 t square. That should be my x. After using the limits, the final answer should be x equals to b square t square by 4. Now I want to substitute the value of t here to get the value, or I want to first differentiate to get the value of v and then substitute for t. So if I differentiate dx by dt, this value of b square by 4 is what will be the constant. So that will come outside of the differential. So outside of the differential I have the value b square by 4. Here also I would have b square by 4. D by dt of t square is 2t into b square by 4. 2 ones, 2 twos, so the answer here is tb square by 2. That's my v. Now when substitute t equals to tau, I have v equals to b square by 2 into tau. This is my answer. So my option should be 2, b square by 2 into tau. Now we could apply the same kind of result to solve this. The velocity v is varying as alpha root x. I'm supposed to find the displacement of the particle with t. What should I do? We'll be going by the same approach. I'll first do dx by dt, which is alpha root x, which means dx by alpha root x should be equal to dt. Now let's compute the integral. The integral dx by alpha root x supposed to be 1 by alpha integral of dx by root x. That should be integral dt. Integral of dx by root x is 1 by alpha x power 1 by 2 by 1 by 2. That should be integral dt, which is t, just like before as we have solved. So x power 1 by 2 is supposed to be alpha by 2 into t. Once again, because x power minus 1 by 2 dx is supposed to be x power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. As we have discussed already, integral x power n dx is supposed to be x power n plus 1 by n plus 1. When n equals minus 1 by 2, just substitute it here. You would get x power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. This is x power 1 by 2 by 1 by 2, which is nothing but the value here that we are seeing. So I would get x power 1 by 2 as alpha by 2 into t. Now I want x. X is therefore going to be alpha square by 4 into t square with the limits 0 to t and 0 to x. I would get here, if I use the limits, x minus 0 is x, t minus 0 would be t. So x is supposed to be alpha square t square by 4. This is something very similar to what we have got it using the 1D motion, which we are very familiar with. S equals to ut plus half at square, right? So such a relation. Now we want how the value of v would change. You notice that v is therefore going to change as dx by dt. So dx by dt is v, which is equals to alpha square by 4 into d by dt of t square. I've already taken this constants outside of the differential. So that would be equals to alpha square by 4 into d by dt of t square is 2t. This is your velocity v. Substituting any given t, you'll notice that the velocity is proportional to t. Thus, we have used the definitions of differentials to solve for these questions. Now let us go to the applications of graphs in kinematics. So whenever you have a 1D motion in kinematics, we are referring to 1D motion as one dimensional motion, that is motion along one straight line. So you could describe entire motion of the object by just defining a particular direction as a straight line. Now you could define the terms distance, displacement, average speed, average velocity in this context of this motion, or in generic as well. Whenever you have distance and displacement and average velocity, there are those are our, we have a terminate the terminologies for the respective motions are all well defined, and we hope we are all familiar with these definitions. We know the average velocity is defined as the displacement by time, which is delta r bar by delta t. In, we'll discuss the vectorial definitions in a while. First, let's understand the term average velocity. It is the total displacement by total time interval. It's not the displacement at a given value by the time at that value. It's the total displacement in an interval of time. Similarly, I could compute the average speed as the distance by time, which is again it's an interval of time. Now for uniform motion, the average speed, average velocity, etc. are all the same. There's not much difference between these terms, but the terminologies will differ once we start defining different kinds of non-uniform motions. Now the acceleration is defined as the change in velocity by the total time taken. So this again is the average acceleration, which is the total change in velocity by the time interval here. We could understand how the instantaneous acceleration could be defined from this. Yes, the instantaneous acceleration can be just obtained by dv bar by dt, as we have seen. There is no square. Now let's apply these definitions and try to understand the key points here for the 1D motion. In 1D motion, we know the distance is always greater than or equal to displacement. Why? First of all, displacement is going to be the shortest distance between the 2 points. So it's a 1D motion. Therefore, we know that we expect the distance and displacement to be both a straight line. Yes, it's a straight line. That's true. But we expect also in a straight line, the length of the path is anyways going to be a same value for distance or displacement. But why is this greater than? In which case can the distance be greater? See, as long as the object is moving in only one direction, the distance should be equal to displacement. But let's say the object goes in one direction and then it turns back and goes in the other. In such case, the displacement is only this value, whereas the distance is basically going to be the entire value. By this, just by seeing this, we can understand that displacement is definitely going to be shorter, lesser than or equal to distance, or distance is definitely going to be longer than or equal to displacement. Now, going by the same definitions, we can say the average speed is definitely going to be larger than or equal to the average velocity, because in the same given time interval, if displacement is always less than or equal to distance, then the average velocity will also be less than or equal to average speed. If suppose distance is greater than displacement, I told you here when is the case when the distance greater than displacement. It is only true that it is true only when the object turns back. That means at least at one point in the path the velocity is zero. Yes, at this point where it turns the velocity is zero, because for turning to happen the velocity has to become zero. All right. The body must have retarded during the motion. Yes, that is true. The body must have retarded because the object has got a the object has moved in one direction and it has become zero, and the object's velocity has become zero from a non-zero value to a zero value. That means there should be a retardation. This is true. Speed increases if acceleration and velocity both are positive or negative. That is true because even if both the displacement and axle and the velo and the let's say the velocity is in this direction, acceleration in this direction. Since both are in the same directions, definitely the velocity will keep on increasing. Let's say the velocity is negative, so it's in the opposite direction. Now the acceleration is also negative. Now still the both of these quantities will aid each other, and these values will increase still. So these all statements apply for the 1D motion alone. You cannot generalize these results for 2D motion. For instance, let's say, if at all the distance is greater than displacement, the object should have at least one point where the velocity is zero. This is not applicable for a case. Let's say, for instance, if the object moves in a circular path like this, in a semicircular path, the object goes from A to B, and at no point the velocity is zero. Still, you will notice that the displacement is always smaller than the distance. So this condition has been satisfied here without the need for fulfilling this consequence. Velocity is never zero here, but still the distance is shorter than displacement, because the displacement is going to be the shortest path between A and B. So we notice that this doesn't apply for 2D motion, because this is a 2D motion going in two dimensions, whereas you can see this is specifically for 1D motion. Okay, so we have already looked at the information from the S versus T graph. Let's use this information from the S versus T graph, and let's use the concepts about curvature to define the A versus T graphs for the respective cases of S versus T. Right? S versus T. Starting from the first, as we see here, we have S versus T, which is a straight line. There is no curvature to this, so the acceleration has to be zero, because it's not a curve. It's just a straight line. A straight line has got no curvature. A is zero. Now this has got a curvature. It's a concave upwards graph. So acceleration is supposed to be positive, right? So let's treat, these are curves representing the motion of an object with constant acceleration, right? Let's not take acceleration to be varying with time. We are just identifying whether the acceleration is positive or negative. That's it. Now in this case it's half a d square. In this case it's ut plus half a d square. But doesn't matter. In both the cases the curvature is upward. So that means the acceleration has to be constant, like this, positive. In this case you have the certain initial displacement is there, but we are not concerned with initial displacement. We are only concerned with the curvature. The curvature is still it's just a it is a concave upwards curvature. So even this graph should have should have the uh, positive acceleration A. Now here you see S equals ut minus half a d square. Here you notice that suddenly it has changed to a concave down or a convex upwards graph. So here the A versus T should be negative. The A versus T will be a negative graph. Similarly, the last part here is once again a convex. It's a convex upwards or a concave down graph. So similarly, even here you will notice that it's once again the graph which is concave down. So the A versus T is once again negative. Right? Alright, so these are certain very important parameters to judge this S versus T, because once we have the S versus T, we could very easily get the A versus T, and from that we could very easily get the V versus T graphs. So for example, if A is 0, the slope is 0, because you see the slope, the V versus T graph can be obtained from the A versus T graph by just simply computing the slope, because you can understand the slope of V versus T is A versus T. And if at all we know the slope from our discussion earlier, when the slope is constant, we know that the graph is going to be a straight line with a positive slope. Then it's going to be theta is going to be acute. And let's say if the graph is s is minus 2t, then the slope is negative. Then in that case, the theta here is going to be obtuse. We know that. So here we can understand if the slope is 0, likewise, if suppose the slope is 0, so s equals to, let's say, constant value, then we know that that graph is just a straight line. So when there is no slope, slope is 0, that means v versus t is a pan. It's independent of time. V is a constant value with time. Now let's take a case where the slope is positive. Where the slope is positive, the v versus t should be a graph which is a straight line, right? V versus t, and compare these two graphs here, because here you have an initial velocity u. This particular graph of v versus t will start with the same slope but from a different point. Wherever you have the u, the same thing will happen. Now in this case, the slope, the acceleration is negative. So in this case, when the acceleration is negative, but there is an initial velocity u, so from the initial velocity, the line is going to have a negative slope, so the theta is obtuse. Similarly here, the v versus t is going to be a graph which has a negative slope, and because it has also got initial velocity, it would be like this. This is a very valuable and this is a very useful thing for the mains. A lot of questions in mains are about the graphs, and we'll understand that all these are basically representing one kind of motion, which is, for example, an object projected vertically upwards. So we'll find that these graphs more or less correspond to this motion, because because we know that acceleration is a constant value for gravity. We take that on the surface of the earth, this acceleration is a constant value. Hence we could apply these particular deductions that we derived for these graphs for a case of a motion of an object that is projected vertically upwards. Definitely we wouldn't be dealing with a case where the acceleration is zero, because this is a uniform motion case. This would apply probably to an object that's moving in space, because the gravity is zero in space. So let's say an object is projected vertically upwards with the initial speed u. The object reaches a maximum height h, and then it comes back. This is height h. The object takes a time ta to go to the top, and then takes a time td to come back. If we call it as the time of ascent ta, time of descent td, then I have to just find the values of ta, td and h based on u and g. Always remember, in kinematics we have the five variables, which is u, v, a, t and s. Out of these five variables, we need three variables at least to solve for the fourth and the fifth variables. So you can understand here, in order for me to find the value of h and the total time here, I need the other three variables. Because t and h are unknown, I need information on u, v and a. So let's say I want to find the maximum height h. The object has gone from here to the maximum height. So the initial velocity, I have an idea, which is u, and I want to find the final velocity. The final velocity at the maximum point is always 0. Why? Because the object is not going any further, which means the velocity here has to be 0, going with the same idea that we have already understood, whereas the body has to have a point where the velocity is 0, and that point is the point of turning, right? So here the object is turning, so when the object turns, the velocity there is 0. Therefore I could say also the value of acceleration here, a is g downward, so we have a is g down. Now all I need to find is the value of s. So we have the relation s equals to ut plus half at square from your basic kinematics. Now the same equation can be represented as vectors, which we'll see shortly. So when I apply this ut plus half at square with the basic sign convention of upwards positive, you'll notice ut and plus half into a is g downwards. Therefore I've got to take it as negative. So ut minus half gt square. This is my s. Now what is the value of t? So I want to find t. Using these three relations, I'll use another equation v equals to u plus at to find the value of t. So how can I find t? I know v is 0, u here is u, a here is minus g into t. So I'll get the value of t as u by g. Now if I substitute in place of this, I'll get u into u by g plus half into minus g into t, which is u by g whole square. So this would turn out to be u square by g. Then here I have minus a u square by 2g square 2g. So u square by g minus a u square by 2g is a u square by 2g. I'm sorry, this is g. So this is minus g u square by 2g square. Square and g gets cancelled. So you have a. So you have u square by 2g. You don't have a here. U square by 2g is your value of the maximum height, h max. So in this scenario, we have computed the h max as u square by 2g, which is something very common that we already know. The the thing to note here is the expression of s. S is varying as ut minus half gt square. So if you just compare it with the kind of the graphs and the expressions we are dealing with, which of these following graphs would correspond to this graph of s versus t? Out of the various graphs that we have dealt with, the s versus t would definitely correspond to such a graph, which is therefore therefore we could say the a versus t, first of all, it's a negative value downwards. As we can see from the sign convention, u is upwards, a is negative, so it's negative value. And the v versus t, v is going to be a straight line which is negative slope, and the s versus t, it's going to be a straight line with a negative curvature. It's going to be a curve with a negative curvature. So it's like this. If it starts from origin, it's going to be like this. Now coming to finding the value of t, since t is u by g, we could say that is ta, the time of ascent to go up. What is td? Using graphical method here, we could say that td should be the same as ta, because the displacement is the same while going up and even while coming down. So the object from the v versus t, we could conclude, because v versus t is a straight line with a negative slope, of course, but because it's a straight line and because the displacements in both these cases are same, this area should be equal to h. So should this area for the return path. Hence I could say that this value of time here should be the same as this time. This is your time of ascent and this should be your time of descent td. Both should be same. Because the simple reason is these two are congruent triangles. As you see, these two triangles have got the same angles and at the same time they've got the same area. Hence they have to be congruent, which means ta should be equal to td, or time of ascent equals to time of descent. So the total time of total time of flight is given by ta plus td, which will be equal to 2u by g, which is something we already know about the 1D motion, where in the case of an object projected upwards, the total time of flight is 2u by t, 2u by g. Alright, so for the various cases of displacement versus time graphs, how can we compute the respective graphs of A versus t? Let's see. So for the object, let's say for the object going from 0 to ta, we know the object has just started its displacement. So the object, it's a negative curvature with with a negative curvature, but the displacement is still positive because the object is going up. And the velocity versus time, the velocity is slowly decreasing from 0 to ta, and finally at ta it becomes 0. The initial velocity is u. So during this time the acceleration is negative, and if you compute the value of the area under s versus t, that should be equal to also the value of the change in the velocity. I'm sorry, if you compute the area of A versus T, that should be equal to the change in velocity, not the area of S versus T. The area of U versus T should be equal to the change in value of displacement. So this area should be equal to this value of the displacement that we have, which is going to be h max here, the maximum height. And this is the initial displacement, which is 0. So as the particle is projected upwards with the speed u, this u corresponds to the speed which is here. The value is u here. And as it goes up to the top, here the value is 0. So we have the 0 for the velocity pointed at 0 at t equals to ta. So the total time it takes to go to this top is ta. So from 0 to ta, the object goes from speed u to 0 with a constant acceleration. Hence it's a straight line variation of this graph. Now because the acceleration is negative, the curvature of s versus t has to be concave upward, concave downwards, or a convex upwards graph. As we have seen, curvature is nothing but d square s by dt square. So that equals to a, and that is negative. Hence it's a convex upwards graph. So it goes like this to the maximum height h max. Note that this is not the trajectory of the graph. Trajectory is different from the s versus t. We have the trajectory where we say that is graph between y versus x. That is trajectory. But this is just a displacement time graph. As you see, the path of the particle is just a straight line, but the graph is not a straight line. Now as the particle goes from the top to comes down, what happens to the path? What happens to the trajectory? Or what happens to the trajectory? Trajectory is still a straight line. But what happens to the displacement time graph? That would continue, because as time is progressing, the graph will also continue. So let's say from t equals to ta to t equals to td. In this interval, how would the curve change? So initially you have the displacement. What is because the curvature is the same, you cannot inflect the point like this. The curvature is same, and the final initial value of displacement is h max. For the rest of the journey, the maximum displacement is where from which it has started with, right? So initial displacement is h max. The final displacement is 0. It has come back to the original point. So the path is going to be like this, with the same curvature, concave or convex upwards. Now what would be the v versus t? Because the velocity is now become is continuing with the same velocity, but in the downward direction. The velocity has changed the direction. V would become negative, and v versus t would be a value like this. This is at ta, and this will be at value td. It's altogether negative value from the beginning, and you can see now, because the acceleration is also negative and because the velocity is also negative, finally due to these both, the displacement is there in the negative direction. Because both are negative, you would find that the value of the velocity magnitude is increasing. Now comes a graph of distance versus time. If I have to plot the distance versus time graph, you will notice that the distance versus time can never become lesser than displacement. So and it can never reduce in time. So during the first part of the journey, the distance and displacement are same, but in the later part, this displacement gets added to this displacement. So therefore, the curve, the same displacement which I have got here has been added to this displacement. I mean, the difference of this displacement has been added to the displacement. Instead of subtracting whatever has been covered from the original displacement of h max, we would instead be adding this upwards. So the particles distance versus time graph would look like this. And the particle speed versus time graph would be like this, because speed can never be negative. Similarly, the acceleration versus time graph would be a constant value like this. Now let's solve some questions on the applications of the respective concepts that we have seen. So all graphs below are intended to represent the same motion. One of them does it incorrectly. Pick it up. So let's see here. Let's understand this graph position versus time. As we see, it is s versus t. It's showing like this. That means it's a case of a negative curvature or it's a negative acceleration. This is v versus t. It's also showing a negative acceleration because the slope is negative. The angle here is obtuse. Let's see this velocity versus position time graph, v versus position. See, this is a unique time graph. We haven't discussed this, but we could just obtain it similarly. That is because for a motion in a motion under gravity, when you project it upwards, you would notice that the slope dv by dt equals to acceleration a. We could also say dv by dx into dx by dt is still your acceleration a. Dx by dt is your v. So you have v dv equals to a dx. So that means the graph of velocity versus, if I do the integral here, I would get here delta of v square by 2 equals to a delta x for a constant acceleration graph. So, or in other words, a graph of y square equals to delta x. It's a graph that looks like this. Because we know for a one-day motion, for every given displacement, you would have two velocities. Once the velocity is upwards for the object going up, and again the object returns back. So that time also for the same displacement, you would have the second velocity downwards. So for a given displacement, you will have two velocities. One is positive and the other is negative. So this is a correct graph for the case where the acceleration is negative and velocity is positive. So this is like a one-day motion graph itself. This could also be correct. But what about the distance versus time graph? We never have a graph which is for this position versus t, which means the initially negative curvature for which you cannot have a positive curvature here. These two are definitely contradictory. So either of this has to be correct. And because this is in tune with this has to be wrong. Because acceleration is negative, you cannot have a distance time graph like this. This is wrong for us. So the option is B. So this question, as you see, has been asked in 2018. Now in this part, we'll be covering all the previous year questions that are asked in graphs. And you would see we would use the same concepts that we have discovered up till now. Now let's take another question. The velocity and time graph of a body in a straight line motion is shown in the figure. The point S is at 4.333 seconds. So here the time is 4.333 seconds. The total distance covered by the body in 6 seconds is. So I have to find the total distance covered. Now it's the distance. For total distance I've got to find the area here, find that particular displacement, and I've got to find the area here, find this displacement and add the modulus of these two values. Because it's distance, I cannot subtract this displacement, because if an object goes from here to here and then returns back, if I plot a graph of v versus t, obviously this displacement would be negative, which indicates it's in the other direction. But when I want distance, I got to add both, just the way areas. And because this is 4.333, 4.333 is nothing but 13 by 3. So I have to just find the area of this trapezoid. Now area of this trapezoid is half a plus b into h, which is half into 13 by 3 plus this side, the two parallel sides. This is 13 by 3 here, this is just 1 here. Half a plus b into height h. Height h is 0 to 4. So it's 16 by 3 into 2, that's 32 by 3. That is the area here. And then you have the area here, which is, this is 6 minus 13 by 3, that is 5 by 3. So the base here is 5 by 3, height here is 2, so half into 5 by 3 into 2, so that's 5 by 3. Now the total distance is supposed to be 37 by 3 meters, this plus this. Let's take another question. A particle starts from origin, from rest, and moves with a uniform acceleration along the positive x-axis. Identify all figures that correctly represents the motion qualitatively. It's a positive x-axis and the acceleration is uniform, and it starts from rest. It starts from rest, then definitely the displacement versus time graph has to start from rest. So this is not an option, this is not an option, these two are not an options. So we have option B and option D. So option A is anyways uh, common for both. Let's verify the B and D. Let's verify just B. B versus T. So it's a uniform acceleration starting from origin, and which has got, which is starting from rest, which indicates v should be equals to 0. We know that it's a uniform acceleration case because that implies basically the v versus t has to be a straight line, and because it's starting from rest, we know it has to start from v equals to 0. Therefore b is correct. Because b is correct, option D is your answer. Let's look at the D option also, x versus t. I can understand because the value of the acceleration is uniform and it is positive, right? So therefore both the velocity and the acceleration are along the same direction, right? Actually in this case the velocity is not there, only the acceleration is creating this velocity. So it's basically a positive curvature case, so it has to look like this starting from this. Option D is also right. Let's take another question. A particle starts from the origin at t equals to 0 and moves along the positive x-axis. The graph of velocity with respect to time is shown in the figure. What is the position of the particle at t equals to 5 seconds? So I got to find the position of the particle at t equals to 5 seconds, and the particle starts from origin at t equals to 0. So as we know, we have discovered just now using the integration, I know the area under v versus t graph should be equal to delta x. So if I compute the area here, that area should be equal to the change in the x coordinate of the particle here. So the area here is from 2 to 5, half a plus b into h should give me 3 plus 5 into the height h, which is 2. So this is the area of the trapezoid, plus area of this particular square is supposed to be 1 into 1, which is 1. That value is going to be 8 plus 1 9, so 9 meters should be my delta x, and since initially it's at origin, the x2 minus x1 which is at 0, so x2 should be equal to 9. So this is my answer. Let's take another question. The velocity time graphs of a car and a scooter are shown here. Now, the difference between the distance traveled by the car and the scooter is in 15 seconds is, so you can notice here the both are starting from rest, and at 15 seconds we got to find the difference in the distance. So basically the difference in the area here is what we got to compute. The car travels the area that is red, let's say this area. The scooter travels the area that is yellow, let's say. So the difference is just going to be this area of a triangle, which is half base into height. If you do base is 5, height is 15, so half base into height is half 5 into 15, which is 112.5 meters. So this is our answer. And for them to catch up, the total displacement should be same, right? Obviously we can understand at this point in time, both the area of the scooter would be this, and the area of the car would be this much more than the scooter. So we go to compute the total area of this and total area of this, and we can compute, we can see that that area would be matching it 22.5. Let's hope so. Which graph, let's take another question. Which graph corresponds to an object moving with a constant negative acceleration and a positive velocity? So negative acceleration, and it's a co- constant negative acceleration. So your velocity versus time cannot be a curve because the acceleration is your slope of velocity versus time. So these graphs are wrong. Now let's take the velocity versus distance curves. So we can know that the values of v versus x, and we could compare dv by dx. So we know v dv by dx equals to a. So we know dv by dx is the slope, which should be equal to a by v, which is supposed to be negative. So between these two, here the dv by dx is a negative value, and here the dv by dx is also a negative value. So both match up. But at the same time, we can understand here the we could see that when the object moves with a negative acceleration, at some point in space, at some point in time in the distance, it has to become zero. It can't become close to zero like this. So this is a case of a, let's compute the we know delta v square by 2 should be equals to a delta x from these two. So we could compare here that the we could see from here that the value of uh, v is varying with respect to x as x power 1 by 2. The value of del v is varying with respect to del x as x power as 1 by 2. So if you choose your initial velocity and acceleration at some point, you need to get a graph which is varying. um, You can see here the value of the slope is decreasing and here the slope is increasing. So now we got to spend that additional amount of 80% of time to get the 20% result. Time to become get a, time to get stuck up, and these are the instances where we waste a lot of time, right? But just to understand the motion of the constant acceleration, we have already seen the graph of v versus x is a graph like this. Now why wouldn't this graph be in this fashion? Because it has to start with a certain velocity. It can't be starting with an infinite velocity, right? With the beginning of the um, at the beginning of the displacement, it can't be having an infinite velocity. So this cannot be a graph of v versus d. So your graph is going to start like this. So this is your v versus d graph. Again, you can see this is a graph which has got a negative curvature. So you can go into d square v by dx square and understand why um, the graph is going to be like this and not like this. Because you can see dv by dx is a, and d square v by dx square, if you compute, that would come out to be uh, minus a by v square, because a is a constant and this is a negative value. Because it's a negative value, the curvature of v versus x is negative, so it's going to be like this. Let's take another question. The distance traveled by a body moving along a line in t is proportional to t cube. The acceleration time graph for the motion of a body will be, so x is proportional to t cube. We got to find a versus t. We know a versus t is nothing but d square x by dt square. It's a twice differential. When you differentiate twice, you're going to reduce the index of the t by 2 times. So you would have a t here. So d square x by dt square, which is a, should be proportional to t, which means it's going to be a straight line. So the a is proportional to t implies it has to be either this or this, either b or c. It cannot be d, it cannot be a. Now out of b and c, C is reducing, B is increasing. Which of these two should the answer be? As you can see here, since the value is positive, d square x by dt square is a positive value, So the A is positive. So if you compute dA by dt, you would get a positive slope of A versus t, because t has got a positive coefficient, which means the slope of A versus t has to be positive, right? Although this is a non-uniform motion and very rarely we discuss the case of non-uniform acceleration, but in terms of graphs it's just the same, because it has got a positive slope, it is just going to be a straight line with a acute angle. Let's take another question. The graph of an object's motion along the x-axis is shown in the figure. The instantaneous velocity of the object at point A and B are VA, VB. Then we can see here, because these are the instantaneous velocities, they should be obtained by dx by dt, and we know dx by dt is nothing but the slope, and the same is true for here, and the slope is nothing but tan theta, and since it's a straight line, the values of slopes at both these points is the same. So vi should be equal to vb equal to the slope, and the slope can obtain by finding this particular relation. 4 by 8 is your tan theta, which is zero point 0.5. So option A. Let's take another question. A body is at rest at x equals to 0, at t equals to 0. It starts moving in the positive x direction. With a constant acceleration. At the same instant, another body passes through x equals 0, moving in the positive x direction with a constant speed. The position of the first body is given by x1 of t after time t, and that of position by x2 of t at the same time. Which of the following graphs correctly describes x1 minus x2 as a function of t? See, x1 is given by half a t square, and x2 is described by, because it's a motion of a body which is at rest, which is at x equals to 0. It starts moving, which means at v equals to 0 also, right? V0 equals to 0 at t0 is 0, and therefore x equals to ut plus half a t square for constant acceleration. So it's just going to be u is 0, therefore it is x half a t square. Now for the second particle, it's moving with constant speed, so its x2 is supposed to be v into t, because it's a constant speed, v is constant, so there is no acceleration. A is 0 this time, so x2 is vt. Now the position of the first body is x1t, and position of the second body is x2t. Now x1 minus x2, which is therefore going to be half a t square minus vt. So it's like a case of a graph which has got velocity and acceleration but in opposite directions. And we can notice that acceleration is positive here, so therefore it has got a positive curvature first of all, and this is a graph with a negative curvature, so this is 0. These two are wrong, we cannot say. Out of this A and B, right guys, so here we can understand first of all, in this for this variable x1 x1 minus x2, let's call it as y, so that is half at square minus vt, and here we have got the relation that it's a positive curvature. And another thing we have is um, we're looking for some more information from this question to decide between A and B, whether it's A B or whether it is A or whether it is B. So I can see here um, that this is a case of half a t square alone. Now I also have a minus vt. How would this graph look like? See, so if I do the dv by dt, dy by dt, if you do the slope of this, so I'm going to have it as at minus v. So I can see at t equals to a certain value v by a, the slope becomes 0. So the slope becomes 0 at least at one point. Here it doesn't become 0 because it's never becoming, the slope is always a positive value and it's keep on increasing. But you see here it became 0, right? So we can be sure that this is that graph. Just to show you further explanation here, see the graph of y equals to 1 by 2 a t square. It's a graph like this. But if I have to subtract minus something like 2t, you'd see it's just, it has to, um, as you can notice here, it's a curve that's going like this. It is becoming 0. The slope becomes 0 at this point. Now we don't have this part, so our curve essentially is like this, right? So our answer should be this one. So it's option B. Body is thrown vertically upwards. Which of these following represents velocity versus time? Velocity versus time. Velocity versus time has got the same acceleration g. This can't be our answer. This can't be our answer. Only option A. Slope has to be constant because in velocity versus time, body thrown vertically upwards, the acceleration is constant, which is g. So your answer is option A. Rubber ball freely falling from a height h equals to 4.9 meters under a horizontal elastic plate. Assume that the duration of collision is negligible and the collision with the plate is totally elastic. Then velocity as a function of time and the height as a function of time will be velocity as a function of time. And so for the object falling from a height initially, the object, the velocity keeps on increasing. Then at one point what happens, the velocity just becomes reverse. Why? Because the object, as soon as it goes and hits the ground, right, it goes and hits the ground at time t1, let's say, it immediately becomes negative like this, right? Because the duration of collision very very small, let's say, so it immediately becomes negative and it starts to go up. So therefore the velocity would be positive and the velocity which is upward starts reducing. So it's almost like the graph that we have seen here, that the velocity has to reduce. So for the next portion of the time, the velocity reduces until the time it comes and until the time it goes to the maximum height and comes back and hits the ground. So the graph is going to be like this. Once it comes and hits the ground, further the once again the direction changes here, and you can notice the graph will therefore be like this, v versus t. To be more precise, v versus t, if you assume the time of collision with the plate is totally elastic and it is negligible, let's say the initial value of velocity, as it is left from the height h, its velocity is negative, so it's starting like this and it starts to increase, and at given point of time it hits the ground, then what happens, immediately it reverses its direction and it goes here. Now it starts its motion like this, and it comes back with a velocity and it hits the ground once again. As soon as it hits the ground, it once again reverses its velocity and goes back. So the correct answer here is supposed to be this. So we have covered all the questions of kinematic graphs that have been asked in 1D motion. So with that, we'll end this work. We'll end this. Thank you all very much.